Okay, so thank you very much for giving me the opportunity to speak remotely. It's not as useful for sharing ideas and perspectives as being there in person, but maybe that will still happen sometime. So I'm going to talk about this concept of spontaneous stochasticity and what we currently understand about it. And I'll just mention at the outset, it's relatively recent, although some of the progenitors of the idea are quite old, back in, well, comparatively in physics, back into the 1920s, around the time of quantum mechanics. But the modern developments of this was in the paper of 1998 by these gentlemen who I pictured here, Denny Bernard, Christoph Kowalski, and Ante Kupiainen, who were studying a quite prosaic engineering problem, in a sense, the problem of turbulent advection of a passive scalar. And they pointed out that this everyday phenomenon required something quite unusual, which I've underlined here in their abstract, the non-deterministic behavior of Lagrangian trajectories at high Reynolds number. And so this was proposed in this paper and then expounded on in many subsequent works, particularly by Kowalski that I've listed here. And so what I'm going to do is I'm simply going to explain what they were talking about and some of the modern developments of this. Okay, so the basic concept here is that of non-uniqueness for the Cauchy initial value problem. And so you can think that you have a velocity field. The simplest situation is an ordinary differential equation with a vector velocity field, and it satisfies some kind of Holder condition. And it's well known in the ODE literature that if H is 1, you satisfy the so-called Lipschitz condition, then there's a unique solution of the Cauchy initial value problem. However, when H is less than 1, there is generally a continuous infinity of solutions. So when there's an infinite number of solutions, there's always a continuous infinity. Then this is called Knesser's theorem. In such dynamical systems, therefore, the Lyapunov exponents are not only positive, but infinity. They're plus infinity. So this sounds like a very mathematically abstract game, but what I'll try to explain is that you see this phenomenon in real physical systems where the Lyapunov exponents are not actually infinite, but merely large enough. And the most standard case where this happens, in fact, is in turbulent flow, where you have little parcels of fluid that move as Lagrangian fluid particles. And it was pointed out here by Onsager in the 1940s that in order to understand experimental observations for such flows, in particular the fact that energy dissipation does not appear to vanish in the limit of very, very high Reynolds number, where the Euler fluid equations become valid, that the Holder exponent cannot remain 1. In fact, it has to be less than or equal to 1/3. And the big question that was addressed by these authors, Bernard, Kowalski, and Kupiainen, is how the particle motion is affected by such roughness of the velocity field. Okay, so to get the idea, the basic idea, one doesn't have to do anything too abstract mathematically. You can get the basic concept from a very simple standard example, where you assume that the particles 1 and 2 are separating according to a velocity field, an increment between the velocity field at the 2 points, which is, I'm assuming, going like the 1/3 exponent proposed by Kolmogorov and Onsager. And then this is a simple ODE that anybody can solve by separation of variables. And there's the exact solution. And what you see is that when time is very much larger than this time that I called T0, which is set by the initial data and the prefactor in this power law, that you go to a long time power law behavior solution in which the initial separation of the particles is forgotten. And this is very, very typical of what happens in what is called spontaneously stochastic systems that does not happen in a chaotic flow. So in a merely chaotic flow, you never forget the initial separation, no matter how long the time is. But correspondingly, if you take the initial separation to 0, then what you find is that this separation between the 2 particles does not collapse to 0, and it remains positive. And that means that 2 particles that start off at the same point still end up at different places in a finite time. So of course, this is exactly the kind of indeterminacy that appears in the classic work of Norton's, the so-called Norton's dome. But what I'll show now is that this is not just a philosophical, sort of game, a philosophical consideration. This phenomenon actually, in some sense, occurs in the real world and accounts for a lot of ordinary everyday phenomena. Okay, so one place in which you can already see this separation occurring, this was the original consideration of Richardson, is in particle dispersion in turbulence, and it's pictured here with this volcanic ash plume. And Louis Fry Richardson, who was a pioneer in meteorology, weather prediction, in turbulence, fractals, many different areas, pointed out this phenomenological relation. He didn't have an a priori theoretical explanation, but he proposed basically by looking at the data that the separation was in fact exactly like this T cubed law that I just derived from that simple model. And in some sense, if you take Richardson's idea seriously, even in the 1920s, you would have been led at the time to the notion of spontaneous stochasticity, but I think at the time it was regarded primarily as a phenomenological observation, and its sort of mathematical importance was not appreciated at the time. This T cube type separation, and more importantly than the power law, is the forgetting of the initial separation, is now seen quite clearly in numerical experiments. And so this is a set of data from a nice paper of Bettani et al. So one of the co-authors of this was Jeremy Beck, who unfortunately couldn't appear, or he would have told you about this work himself. But here it's shown a turbulence simulation, and the mean square separation between the particles for various initial particle separations. So as we're going from green to red, the particle separations initially are getting smaller and smaller. And what you can see is that at a given finite time later, as you let the initial particle separations go to zero, the particle positions at the later time stay at the same mean square separation. They do not get smaller and smaller. And so you completely forget the initial separation, and you end up with a finite separation at the later time, which is independent of that initial separation. So I should mention that this has still not been unambiguously seen in laboratory experiments. And this doesn't seem to be due to any matter of principle. It's just due to the severe technical difficulties in tracking very many close particles over long enough time intervals. So I know many experimentalists that are still trying to see this, but it's very difficult to do in a laboratory experiment. But numerical simulations with Navier-Stokes turbulence see this quite clearly. Okay, so this was basically the setting in which Bernard et al. Worked, and they were considering the problem of taking this turbulent flow and putting in a Brownian particle. So a simple example would be a perfume molecule. And so you take a perfume molecule, a heavy aromatic molecule, you put it into the flow, and it's advected both by the turbulent flow, but it's also undergoing its own turbulent Brownian, its own molecular Brownian motion with diffusivity D. And what they wanted to understand was various properties of the statistics of the passive scalar of this ensemble. It's not really an ensemble, it's a collection, a distribution of the molecules that is advected by the turbulent flow. And one thing you can do very simply is write down a path integral representation of the probability at any given later time. So this is analogous to a Feynman path integral, but it's really a Wiener path integral. It's a perfectly well-defined object. And what you see is that this Feynman-Katz representation of the probability is in fact given by the deterministic part of the time evolution squared, so that if you take the limit where D goes to zero and you go back to the deterministic evolution, what you would expect is that you will collapse to a single deterministic trajectory, which is just the solution of the ordinary differential equation without that extra Brownian particle there. Okay, and so this is the naive expectation, and that is indeed what happens if you keep the viscosity of the fluid also fixed, that is the Reynolds number. But if you take the limit of high Reynolds number and small diffusivity simultaneously, then what Bernard and the others found in a simple model, the Kriknen model, is that that's not what happens, is that the particle distribution stays random. And the limiting distribution is now a non-trivial distribution over non-unique solutions of that limiting singular initial value problem. And so this is a breakdown of usual Laplacian determinism for classical dynamics. So just to give you a simple intuitive picture of this, the case where there's no spontaneous stochasticity is on the top. And this would include something like standard chaos. So with standard chaotic dynamics, if I let so I have a smooth laminar flow, for example, I can take the viscosity getting smaller and smaller. I can take the diffusivity getting smaller and smaller. And eventually I just see one deterministic trajectory. And in fact, in the examples of the three-body gravitational problem that we heard about earlier from Charda, this is essentially what happens there. They're seeing something that appears to be standard chaos, although perhaps of a somewhat unusual variety. But in any case, standard chaos in which if you take the noise small enough, things become essentially deterministic. But that's not what happens in a spontaneously stochastic system. And the second diagram illustrates what happens there. Now you have non-unique solutions of that limiting singular dynamics, and generally not three, as I've shown here, generally a continuous infinity of them. But as you let the noise get weaker and weaker, you never show any tendency to become deterministic. You stay random, and in the limit, what you see are the solutions of that limiting singular dynamics with certain probabilities. And they're actually, for statistical physicists, sort of close analogies with disordered systems like Sherrington-Kirkpatrick model, where you have non-unique ground states of the Hamiltonian. Here, they're non-unique action minimizers of that action. But in any case, this is the essential phenomenon of spontaneous stochasticity, which I think the terminology spontaneous stochasticity seems to have first been used in this paper of Falkovich, Goetsky, and Vergasol in Reviews of Modern Physics in 2001, where they said the spontaneous stochasticity of fluid particles seems to constitute an important aspect of developed turbulence. So what was really fundamental about this work was not only that they pointed out this phenomenon happens, but it has very important empirical consequences. So one of the things that's observed in turbulent flow is that the mixing of scalars is also independent of the molecular diffusivity. And this is a very common experience. I mean, there's detailed experiments. I list them down here at the bottom if you want to read about more detailed experiments in this by Donzis et al. In Journal of Fluid Mechanics. So they discuss both numerical and laboratory experiments that show this. But in a turbulent flow, the mixing of a passively advected scalar appears in the limit of very large Reynolds number and very small molecular diffusivities to remain finite and independent of that molecular diffusivity. And what they pointed out in this paper is that, in fact, that's in order to understand that, you require this Lagrangian spontaneous stochasticity. So in addition to proving that it occurs in a particular solvable model, they gave a very general argument that says whenever you have anomalous dissipation, there must be Lagrangian spontaneous stochasticity. There is no other way that you can get this mixing of scalars independent of the molecular diffusivity without it. And it's a very simple argument simply by using this Feynman-Katz representation, taking the limit, and if everything collapsed to a single trajectory, then you would find that the concentration of the scalar at one later point at a later time would just be what you saw by the advected scalar along that particular Lagrangian particle path at the initial time. But in order to get a decrease in that scalar concentration, that is due to the mixing, the RMS value goes down, the only way that can happen is if these trajectories stay random. And this can actually be made into a rigorous mathematical theorem that says that the only way this can happen is by the particle trajectory staying random. So a very prosaic fact that you can smell somebody's perfume or cologne when they enter the room is due to this bizarre or apparently bizarre breakdown of determinacy, because molecular mixing would take months for a heavy aromatic molecule to diffuse several meters. And the fact that you can smell it in a reasonable amount of time is because there's small scale turbulence in the room. Okay, so this idea, as I said, goes far beyond the Crichton model in which they first worked it out. And they considered many other soluble or semi-soluble models. I worked it out, I think, for the first case of a deterministic PDE, the Burger's equation, where there is no, we would now call Eulerian spontaneous stochasticity, that is for the velocity field itself. And that's relevant to the cosmological issues that Mark was talking about, because the adhesion model in cosmology is just the Burger's equation. That's totally deterministic. There's no spontaneous stochasticity there, but there is spontaneous stochasticity backward in time of the Lagrangian particles, and that is what leads to the anomalous dissipation for the Burger's equation. So that was sort of the first simple example of for a deterministic PDE showing that this phenomenon occurs. But this phenomenon also happens far beyond hydrodynamic turbulence. And I think that Ethan will be talking more about some of this. In addition to having Feynman-Katz type representations for scalar equations, you can also use them for vector equations. And so here I've written down the magnetic induction equation as it appears in magnetohydrodynamics. And you can very simply write down corresponding path integral representations for the magnetic fields, in which you find that the magnetic field, the resultant magnetic field at the final point at the final time, can be obtained by going backward in time along these stochastic trajectories, sampling the initial data, and then transporting them, stretching and rotating along those trajectories to the final point, and then averaging. And that gives an exact mathematical representation of the solution of this equation. And the standard knee-jerk assumption has been that as the plasma resistivity gets smaller and smaller, that this would be more and more just one trajectory, and classical frozen-in property of the magnetic field would hold. But in fact, what was done in this paper with Ethan and others was to show that in magnetohydrodynamic turbulence, that's not what happens, and that you have Richardson type dispersion of these trajectories. And so you'd never get classical frozen-in properties of the magnetic field in such a turbulent plasma. So there are implications beyond just scalars. But it also has an Eulerian aspect. And this is the work primarily, I should say, of Alexei Malayev and his collaborators. Here's a very nice example taken from the paper of Thalabard, Beck, and Malayev, in which they looked at a simple Kelvin-Helmholtz unstable vortex sheet. So you have a velocity going one way at the top and the other way at the bottom, and a vortex sheet in between. And if you regularize this by putting a little bit of viscosity and also a little bit of noise, what you see is that this evolves into this mixing layer. But in fact, it does so in a very indeterministic way that never becomes deterministic as you let the noise get smaller and the regularization of the velocity field get smaller. And this is related to known mathematical results for this problem, where it's known that if you remove those regularizations and the noise, you converge to so-called weak Euler solutions, that is distributional solutions of the Euler equations that I pictured here. But it's also known that there are many more than one Euler solution for such vortex state initial data, even if you impose that they be locally dissipative. And this is part of the work on what's called convex integration theory, of which Laszlo Szekelydi is one of the pioneers. So this is the ingredients that you need also for what I now call Eulerian spontaneous stochasticity. And this is the same thing that happened in the Lagrangian case. The limiting singular equation has now non-unique solutions. And now, even if you don't have infinite Reynolds number, you have finite but large Reynolds number and small but finite noise, then you can get indeterminate phenomena that don't disappear in the limit. And that's what they clearly observed in this flow. Whereas if they looked at the energy RMS value between two different solutions, so this is sort of the energy norm distance between two independent realizations of this flow, then as they decrease the regularization, that's this parameter nu, and as they also decrease the noise that they put into the system, that RMS value does not vanish. It's the exact analog of Richardson dispersion, but now for whole velocity fields. And you go over to this, in this case, a not TQ, but a linear power law. But the important thing is not the power law, it's that you go to the same power law no matter how small the noise is. Okay, and so that was this, this important paper here. This actually, I mean, how much time do I have? I want to make sure that I can cover everything. How much time do I have?
20 minutes.
How many?
20 if you leave just 5 minutes for questions.
Okay, so I think I can do it. So I just wanted to cover a couple more points. So one point was that in this paper, they did not use sort of realistic noise. They put in just sort of an artificial ad hoc noise. But in the real world, there is a noise that's essentially unavoidable whenever you have hydrodynamic description, which is molecular or thermal noise. So this is intrinsic to the validity of a hydrodynamic description, because in order to have a hydrodynamic description, you have to have local thermodynamic equilibrium. And whenever you have local thermodynamic equilibrium, that means that the molecules have equilibrium statistics in which there are known thermal fluctuations. And so one of the questions that we answered in our recent work that I'm going to tell you about now is, are thermal noise enough? Is small molecular fluctuations enough in order to give you spontaneous stochasticity? And so we know how to model such thermal noise. This was already done by Landau and Lifshitz in the 1950s, and there have been many experimental tests of their theory, and it's always worked. And so what we followed is we simply took that standard Landau-Lifshitz fluctuating hydrodynamic description, in which you put in an extra noise term, which looks like a white noise in space and time. It's actually not. There's a cutoff. This is in the language of physicists, an effective field theory. You don't want to take that cutoff lambda going to infinity. You would run into horrible ultraviolet divergences then, but it's not even physically meaningful to do that, because this equation doesn't hold when you get down to scale smaller than the mean free path. So this is some cutoff which is more or less arbitrary. But in any case, you take this standard set of equations, and now we non-dimensionalize that as one usually does in turbulence, with a large scale length scale and a large scale RMS velocity field. And what you find is that, just like Navier-Stokes, the viscous term on large scales is negligible. So it goes like 1 over the Reynolds number. So this is exactly the basis of the statement that I made earlier, that the large scales of a turbulent flow are described by Euler equations. And so the viscous term drops out in the limit of, it's never exactly 0, but it becomes more and more negligible as the Reynolds number gets larger and larger. And the noise term is similar, but it's even smaller, because not only is there a large power of Reynolds number in front of it, and that's because there's a fluctuation dissipation relation that governs the thermal noise, that says that the strength of the noise is proportional to the viscosity. And that means that's also tied to the Reynolds number. But even taking into account that factor, there's this other factor, theta k, which is physically the energy in a little Kolmogorov eddy. So this is the so-called Kolmogorov dissipation scale. If you look at the amount of hydrodynamic energy in that little Kolmogorov eddy, and you compare that with the thermal energy, this is that ratio. And that's also an incredibly tiny number for every, for ordinary flows. So in the atmosphere, for example, it's about 10 to the minus 8. The thermal energy is really tiny, even compared to the energy of a Kolmogorov scale eddy. So this is a really, really tiny quantity. And again, in some sense, you are justified in neglecting it in the limit, but precisely the question is, can it be really entirely neglected, or does it have consequences even though that term formally vanishes, are there consequences for the solutions in the limit? And what I'm going to try to convince you is that the answer is yes, that there are consequences that remain. So we can understand this problem in exactly the same way that we looked at the problem of Lagrangian dispersion, and we can write down a path integral representation. In this case, it's even better than Feynman's. I mean, it's all Euclidean in the language of quantum field theory. There's no mathematical problems. You can make rigorous mathematical sense of this. And in fact, in the literature, there are rigorous mathematical derivations of this action as a large deviations rate function. Actually, those are misleading. I'm not going to go into that here. I just wanted to make a remark that those rigorous derivations are actually wrong and they make a wrong prediction. But I don't have time to go into that here. The important thing is that they're trying to make sense of this in the case of lambda going to infinity. And if you keep, as a physicist would, lambda strictly finite, you don't need any of the fancy mathematics that they use to derive this result. And in fact, with their fancy mathematics, you make physically wrong predictions, but that's another story. Okay, the important thing is that when you take this action, and if you just naively do a steepest descent approximation on it, just like in the case of Lagrangian particle dispersion, you expect to see the unique solution of the limiting singular equation, which is now just the Euler equation with this external force. And if that singular solution has one solution, then you'll just see deterministic behavior essentially in the limit. And indeed, that's what would happen if you were considering a laminar flow. Then there will be a nice unique solution of that Euler solution. It will be nice and smooth. But for turbulent flow, that's not the case. And this again goes back to the fact of what Onsager realized, which is that for turbulent flows, these limiting Euler solutions are dissipative. They continue to dissipate energy, even in the limit of infinite Reynolds number. And what's known based on the work of the convex integration theory coming from John Nash's ideas is that you have this Nash non-rigidity, which means that those limiting solutions are wildly non-unique. And so here I list some of the recent papers about that, where it's now known that you get non-uniqueness even up to the Onsager critical exponent. That's this latest work by Denary et al. And even if you impose that the solutions are globally dissipative, then you have infinitely many non-unique solutions of this equation. Okay, but what we want to do is we want to understand what happens in the presence of thermal noise. So what I'm going to talk about very quickly is a numerical experiment. And we make a so-called shell model version of this because with present-day computers, nobody in the world can solve this Landau-Lifshitz equations at the high Reynolds number needed to study the phenomena I'm going to talk about. And so we take the expedient of using this so-called shell model, which has the same general features as Navier-Stokes, including turbulence and dissipative anomalies and Kolmogorov spectra. But because it only has one mode per every dyadic shell, it can be simulated to very, very high Reynolds numbers. And we add in a suitable noise that we choose to have the same scaling as appears in the 3D case. So all the scaling in this study that I'm going to describe is exactly as for the 3D case. And now we can simply study this in the limit of very, very large Reynolds number, where it's known that in the infinite Reynolds number limit, again, you get weak solutions of the inviscid limiting equations, but those are not unique. And so we have all the ingredients again for spontaneous stochasticity. So what we find when we do this study is that the noise doesn't vanish, and there are several simple ways of measuring that. One is by looking at the total variance. That's analogous to what Richardson did, and also what was done in the earlier work of Thalabart et al. for the Cohen-Helmholtz unstable shear layer. So that's just like the L2 energy norm, and that's what I'm showing here is that growth of that norm. A more refined measure is the energy spectrum itself. That's what I'm showing here on the right. And those are the individual terms in that sum. So for each shell, I can look at the variance in that shell as a function of time. And you can see the growth of that variance across the shells over time. And then this this kind of diagram actually goes back, as I'll mention in a moment, to the early work of Lorenz in the 1960s. So let me actually just discuss briefly some of this classical work, because this subject did not begin with our work. David Ruel considered already in a paper in 1979 possible influence of microscopic fluctuation, thermal fluctuations on turbulent flow. And he realized that because of standard chaos, thermal noise would grow to be important at the Kolmogorov scale in about a Kolmogorov time. And in fact, this parameter that appears here in his paper is exactly related to that parameter that we call theta K. And this is just the time that it takes for a thermal fluctuation to grow to order the Kolmogorov scale. And that is the Kolmogorov time up to a factor that depends logarithmically on this parameter theta K. So theta K is very tiny. However, when you take a logarithm, even of a very, very big number, it gets pretty small. And so within a factor of maybe like 10 Kolmogorov times, molecular noise gets carried to that scale, to the smallest scale of the turbulent flow, the Kolmogorov scale. But then the ideas of Lorenz come in. And it turns out that Ed Lorenz probably should be considered as the person who came closest to understanding what we now call spontaneous stochasticity before anyone else. And many of the essential ideas of spontaneous stochasticity are outlined in this very important paper that he wrote in 1969. I should mention, by the way, this has been heavily advertised by Tim Palmer, and we completely agree with him. This paper has been—
I just heard that.
Yes, this paper, the importance of this paper has been overlooked, and Palmer has been justly going around telling people this is much more fundamental and much more revolutionary than his 1963 paper. And this is what Palmer calls the real butterfly effect. Because when Lorenz talked about the butterfly effect, he was talking about the results of this paper, not the 1963 paper. And just
We'd also benefit from listening to your own opinion, Greg.
Yeah, okay. So I think the Lorenz, I'm just going to read what he says here because it shows how clearly he understood these issues. He said, it is proposed that certain formally deterministic fluid systems, which possess many scales of motion, are observationally indistinguishable from indeterministic systems. Specifically, that two states of the system differing initially by a small observational error will evolve into two states differing as greatly as randomly chosen states of the system within a finite time interval, and that finite time interval cannot be lengthened by reducing the amplitude of the initial error. And that's the essential distinction that he was drawing between this phenomenon and his earlier work, where in a chaotic flow, there's a horizon of predictability which can be made arbitrarily long by simply making the initial error sufficiently small. And what Lorenz was pointing out is that in flows of the turbulent type, this is not true. You get a horizon of predictability which does not get lengthened as you reduce the amplitude of the initial error. And that's exactly what we're showing in the results here. So, I mean, let me just go back and talk about this phenomenon we're seeing here. So this earlier, this L2 error growth on the left, you see at early times just linear diffusive growth. That's just purely from the thermal noise. Then you see exponential growth, and that's the Ruel exponential. And then at late time, you see the Lorenz phenomenon, and as it was worked out in more quantitative detail by Crichton and Leith, you see a linear power law growth of this L2 error. But what was especially seen in Lorenz's work is how this error spectrum grows in time. It grows by what Lorenz called an inverse error cascade. And this is exactly analogous to what was shown in Lorenz's paper in 1969 as figure 2, whereas this error grows stepwise backward in time from small scales to large scales as the uncertainty propagates from the very small scales by this inverse cascade up to the large scales of the turbulent flow. Okay, so by the way, the simulations of our shell model simulation here were done with the parameters of the atmospheric boundary layer. And the only source of noise in the simulation data I'm showing you is arising from thermal noise at the temperature of the atmosphere. And so what we're seeing is that molecular fluctuations, the fluctuations of the molecules themselves, leads to large-scale indeterminacy. You don't need the flap of a seagull wing. You don't need microorganisms, swimming around in the ocean. Those are much bigger perturbations that exist, but in fact, the intrinsic thermal fluctuations themselves suffice. So in fact, to show that this is really spontaneously stochastic, we study carefully the Reynolds number dependence. And we study the randomization time. So at any one of these scales, we can say how long does it take in order to become totally random. That is, that the variance becomes some set fraction like 1/2 of the final energy value. And we call this the randomization time. And those randomization times are plotted here as a function of scale. And the important thing is this inset, which looks at one particular shell. And what you see is that this randomization time in the limit of very large Reynolds number saturates to a constant value, which is not 0. And it's approximately given by 3.4 local eddy turnover times. So that means in the limit of very large Reynolds number at any scale of motion, in about 3.4 eddy turnover times at that scale, the dynamics is totally random. And it cannot be made less random by taking higher Reynolds number, which means smaller noise. Okay. And in this limit, you get non-trivial statistics. So if I look at one given shell at a fixed time, as you let the Reynolds number get higher and higher, and here we're varying over a factor of about 2 orders of magnitude of Reynolds number, the statistics are completely universal and totally independent of the Reynolds number. And so again, I recall the statement of Lorenz that these are formally deterministic fluid systems in the limit, governed by this envisaged shell model dynamics, but they're observationally indistinguishable from indeterministic systems. And you cannot make the error smaller by reducing the strength of the noise. It stays random. Okay, so I'm just going to try to end up very quickly with a brief discussion of what happens with quantum case, because you might say, well, what if we go to absolute 0 and we get rid of thermal fluctuations? Could we still have spontaneous stochasticity? And then, of course, even if you go to absolute 0, you'll still have quantum fluctuations. So I looked at this in work that I did some years ago with my then student, Theo Drivas. And we looked at a very simple problem of a cusp potential. This is very similar to potentials that have been studied in inflationary universe scenario, the inverse Gaussian case or inverse oscillator, but with a crucial difference that here our alpha is less than 1. So that means our Hamiltonian dynamics, again, have this indeterminacy. And if we take the singular limit with this cusp potential, there are infinitely many solutions, but here I show you the 2 extremal ones. Those are the ones that go the furthest to the left and the furthest to the right at that given time t. To make this physical, we don't want to have a real cusp, and we don't want to go down to the Planck length and below. We want to have a nice smooth potential, but we're going to consider a limit in which as h bar over m gets smaller and smaller, and we're approaching the classical limit, simultaneously, the potential is getting more and more singular. That's the kind of limit in which you get this spontaneous stochasticity. Okay, so that's the question. If I do simultaneously h bar over m getting smaller and smaller, but I simultaneously make the potential closer and closer to the cusp, which classical solution will the quantum wave packet follow? So there are many semi-classical limits, but we decided to, in our paper, we analyzed several, but the best analytical results were for the WKB limit, in which you take h bar over m going to 0 first, and then we let the uncertainty of the wave packet shrink to 0. So we're starting off with a minimum uncertainty wave packet, and then we just apply standard time-dependent WKB, and here it's all written out. I think this is familiar to everybody here. You actually get the WKB solution by solving the classical equations. The density, the probability is given by solving those trajectories and finding the Jacobian, and then just evolving the probability along the classical trajectories, and then the phase of the wave function is given by the classical action. Okay, so this is what we did for this particular problem. And what I'm going to show you first is the evolution in dimensionless time for a fixed fixed value of h bar over m and a fixed value of, well, actually, we've taken h bar over m, I should say, to infinity, to 0 first. So this is WKB. So we've taken that off to 0. But then I'm going to evolve in this dimensionless time here with a fixed value of that smoothing parameter and also of the width of the wave packet. And if I do that, what you see is that wave packet splits into two. And here are the two classical solutions in red. And I think you can see that the peaks of the wave packets, and here I did two different regularizations. That's why I have two different plots. And the peaks of the wave packet, independent of the particular regularization, follow more or less those classical trajectories. But the really essential question is, what happens if I take the limit where sigma and L go to 0? And does the motion remain random? And that's what we see in the second movie, where now I'm going to look at that fixed time t later, and I'm going to let the width of the initial wave packet shrink to 0, while simultaneously the potential becomes more singular. And then you see what happens is that the wave packet shrinks to essentially two delta functions. It does not become deterministic. You still have randomness even in the semi-classical limit, where now you're talking essentially about infinitely massive objects. These could be, supermassive black holes. But in this kind of potential, you have remnant indeterminacy, whose ultimate origin is just quantum indeterminacy, but it's magnified to the macroscopic level by this singularity. And so the kind of spreading of the wave packet that you see is now remarkably like what you see in a turbulent flow. It's this Richardsonian type of spreading, and this is quantum spontaneous stochasticity. So again, if I had textbook spreading of a free wave packet, I would never see anything like this. If I just took the textbook spreading, if I take h bar over m going to 0 first, this factor is gone. Then if I take sigma goes to 0, I can make that as small as I like. So if I did the same limit for a standard free wave packets or for a wave packet in an inverted oscillator potential, none of this would happen. This requires this approximate singularity to be there in order to get this quantum spontaneous stochasticity. So let me just say very quickly that this could happen in the laboratory. Probably the simplest case where this could happen is in superfluid turbulence at 0 temperature, or as close to 0 temperature as you can get, where we know that there are quantized vortices, and they are advected by the superfluid vortice, the superfluid velocity. And in fact, with some types of superfluid turbulence, you see, as I show here, a Kolmogorov spectrum. So there are many different types of quantum turbulence. There's a very, very recent preprint by Berengi et al. That nicely reviews the different types of quantum turbulence that appear in laboratory superfluids. And the one that I'm going to be particularly interested in here is the one where the large scales of the turbulent flow are more or less classical, and you see a Kolmogorov spectrum. And in those turbulent flows, what you see are bundles of quantized vortices that act more or less like classical vorticity. Now, putting these ingredients together, what you expect here is, in fact, that if I look at two of those quantized vortices, there should be some kind of Richardsonian dispersion, and they should separate according to this probabilistic Richardson dispersion. And so one expects that the vorticity in superfluid turbulence is subjected to the same kind of spontaneous stochasticity effect that we saw earlier in the work on magnetohydrodynamic turbulence with Ethan, that I think he'll tell you more about. And so this is actually something that has not yet been seen either numerically or experimentally, but it was proposed in particular in this paper in JFM that I wrote in 2020. So I think it's the most likely situation to observe this effect experimentally in nature. Okay, so this is basically the end. I just want to say that this is still a very much developing subject, and there's a lot of work. that's ongoing. It's hard. I mean, there's, unlike many other areas of physics, I mean, there's no small parameter. Everything is non-perturbative. It's strong coupling. When you want to try to understand something, every model has to be solved analytically or some other way, numerically. And so it's hard going, but there's a lot of ongoing study of model problems where it's been shown that this phenomenon does exist. There's related mathematical development in the PDE community, studying these things through methods of convex integration and Nash's ideas. There are close connections with weather and climate modeling, in particular related to Hasselmann's work, and potential corresponding implications for astrophysics and cosmology. I mean, really, the essential question is the goal of numerical modeling in astrophysics and cosmology more like classical celestial mechanics, where you think, okay, I'm going to predict one thing that's going to happen, or is it going to be more like weather prediction, where you want to do ensemble forecasting? And there are also lots of other interesting connections with statistical physics. And I'll just mention one thing I didn't have any chance to go through here at all in this cursory summary is one recent development is the beginnings of a development of a general renormalization group theory of this phenomenon. And here I just cite two works on developing renormalization group ideas for this. And so let me just end this talk by dedicating this talk to the memory of Krzysztof Gołęcki. He tragically died last January from a combination of cancer and COVID. But was a brilliant mathematical physicist, and he was probably more responsible than anyone for the modern understanding of this phenomenon of spontaneous stochasticity. So thank you.